Recording, Marcia.
Okay.
So good afternoon, everyone. It's a pleasure to have you all here, especially to have Professor Matthias Hieber with us. He is from the Technical University of Darmstadt, and he's a leading expert on PD, especially on fluid dynamics and functional analytic methods. Over the years, he has been working with particular equations or like Navier-Stokes, but recently he has been developing mathematics on geophysical flows. And today he's talking on analysis of these geophysical flows. And we are very glad to have you here. And we are glad that you can share us a little bit of what you have been developing. And Professor Hieber, the screen is all yours now.
Yeah, thank you very much for the kind invitation and for having the opportunity to give a talk in your seminar over here. That's a great pleasure and honor to me. So my talk is about, as you were saying, geophysical flows. And what I'm going to talk is joint work with a couple of essentially younger people. It's Antonio Agresti, who is now professor in Rome. It's Tim Binz, who is postdoc in Princeton. It's Felix Brandt, who is postdoc in Berkeley. Amaru Hussein, who is professor in Kassel in Germany. Yoshiki Ida is postdoc in Tokyo. Anna Breu is professor in Spain, in Bilbao, and Tarek Zöchling is a PhD student. So what I'm going to talk, I would like to introduce geophysical flows, and let me then start with the balance law for fluids, compressible or incompressible. So then we have the standard balance law for momentum, mass, and energy, and you all know them. First one is the balance law for the mass. Second one is balance law for the momentum, and the third one is the balance law for the energy. And this system is then completed by boundary conditions of Dirichlet time for the velocity and Neumann type for the heat flux. So here U denotes the velocity, rho the density, and pi the pressure of the fluid. On the right-hand side in the second line, we see divergence of S. S is the associated stress tensor of the fluid. E is the internal energy, and we are looking at that in a bounded domain. So far, we did not specify the stress tensor, but let me then tell you from the beginning. So if we define the total energy as the kinetic energy plus the internal energy, and we call it E, then we see that E satisfies a certain equation, which is down there, over here. And now if you integrate this equation, we see that the energy is constant, provided we have this type of boundary conditions we were assuming. And this means independent of the choice of the stress tensor, independent of the choice of the heat flux, the total energy of this type of fluids is always preserved. Now, to make it more interesting, now let's look at examples of typical stress tensors. And if we start now with the isothermal incompressible situation, so we assume that temperature is constant, we assume that the density is constant, then there are the classical laws due to Stokes and Fourier, and then we get the usual stress tensor, which is also called Cauchy stress tensor. It's 2 times the deformation tensor over here. And one sees this is then consistent with the second law of thermodynamics if certain quantities mu s and mu b satisfies the well-known relationships. Now to coming from this situation, how to get to this well-known equations of fluid dynamics. So if we choose the stress tensor to be equal to 0, then we obtain Euler's equation. If we choose a Newtonian or Cauchy stress tensor, we obtain the equations of Navier-Stokes. If we add an elastic part, then we end up with the Oldroyd B type of fluids. One can also look at non-Newtonian stress tensor where the viscosity function depends on D. And what we are doing here now in this talk, we look at a particular stress tensor describing the primitive equations, and they are prototype for many equations in the geophysical sciences. Okay, for the non-isothermal situation, let me recall that there's also the well-known Boussinesq equation, which we will discuss in a second a bit more in detail. So now, how do these incompressible primitive equations look like? Let us start with the anisotropic Navier-Stokes equations. So anisotropic means we have different viscosity coefficients in the horizontal and the vertical direction. So let's assume we have the Navier-Stokes equation, and in the horizontal Laplacian we have a viscosity coefficient 1, and in the vertical one we have a coefficient epsilon squared. And we look at this in a epsilon dependent domain, and for simplicity we take the unit square times the interval minus epsilon to epsilon. Now one can introduce new variables scaled like written down here. And if you start with this anisotropic Navier-Stokes, we end up with an equation for the horizontal viscosity, which reads like this over here. And for the vertical viscosity, we get a term epsilon squared times the terms in the bracket over here describing the vertical viscosity plus the vertical derivative of the pressures equal to 0. So now this equation is now defined on a domain independent of epsilon. So now it's tempting, if you see the epsilon squared in front of the terms in the brackets, it's now tempting to take at least the formal limit over this equation. And if we take the formal limit, then we see from the first line we get Vt plus u times gradient V minus the Laplacian of V. And now we get the horizontal gradient of the pressures equal to 0. And we see that the vertical derivative of P remains above here is equal to 0. And we have then the divergence U equal to 0 condition. So then this is now, let's say, a variant of the Navier-Stokes equations, where, as you can see, the pressure term is different. The pressure term is easier. It just depends on two variables. However, the nonlinear term is more complicated. Now you may ask whether this formal computation can be justified rigorously, and indeed there are, you see the names down there. There are results by people listed down there who gave a rigorous justification of this limit procedure. Yeah, and then we call that the primitive equations. And they are interesting because they are the building block for many geophysical models. So now we can see, the picture is unfortunately not very easy to read. It's from the original of Lyons, Temam, and Wang. They describe coupled atmosphere-ocean models, and they take for the atmosphere a primitive equation and for the ocean a primitive equation, and then they couple it. We will see in a second in more detail. You can also look at different coupling conditions and other forces, and the forces can be either deterministic or stochastic. One can now look in the setting of primitive equations at the situation of moving interfaces, free boundary value problems like the ocean, or one can look at fluid structure interaction, and you can make it even more physical. You can do phase changes. So the water in the atmosphere has different components in clouds and in moisture and in real water. And one can do, again, a stochastic component, including transport noise in this equation. So I will discuss some of this issue in the talk over here. So let me now introduce to a classical model which goes back to Lyons, Temam, and Wang. And they described in the 90s a model which is a coupled atmosphere-ocean model. And it can be roughly speaking described as follows. So we describe the atmosphere by the compressible primitive equations. And we describe the ocean by the incompressible primitive equations. And then at the interface, we have to find appropriate coupling or interface conditions, and we will call them wind-driven boundary conditions following Lyons, Temam, and Wang. So what is the law, the physical law behind these boundary conditions? So one can say that the driving mechanism at the interface is the following. We say that the shear stress of the ocean equals the horizontal wind force. So that's the physical law behind this boundary condition. And now you can calculate the shear stress of the fluid. And because we are dealing with a flat interface over here, you can see that the shear stress is of the form d that v plus gradient w. And the gradient w is vanishing due to the flat interface. And then on the left-hand side, we have then that the dz of the velocity of the air is minus of this of the ocean. And now we have to model the wind force. We have to model the horizontal wind force. And there is a whole theory in physics, and it's described like this. So it's the difference between the two velocities times the absolute value of the two derivatives to some power alpha. Yeah, and then we have a boundary condition which is usually called of wind-driven type. And now if we distinguish between various values of alpha, we see if alpha is equal to 0, we would have a linear boundary condition. If alpha is equal to 1, we have a fully nonlinear boundary conditions. And let me tell that in the particular situation of a linear coupling, this type of boundary condition was already investigated in detail in the situation of Navier-Stokes by the French school. You can see in the names over here, and they did a careful analysis in the case of the Navier-Stokes equation, but also in the linear case. So our aim here is to look at the original model by Lyons, Temam, and Wang, and to analyze that not in the weak sense as they did, but in the strong sense. So let me then describe the model in more in PDE terms. We saw that we would like to model the atmosphere by a compressible primitive equations. And then they introduced a new system of coordinates, which is nowadays called the pressure P coordinate systems. And the ocean is modeled by the incompressible primitive equations in usual coordinates. And then if we write down the system, we see we have here the primitive equations in these new coordinate systems. We have a boundary condition of wind-driven time, which we just studied, and we take alpha equal to 1, so we take the fully nonlinear case. And then the same is true for the ocean. We have here incompressible primitive equation, and we have this type of boundary condition also for the ocean, and they are then mixing over here. So what are the unknowns? The unknowns are the velocity of the atmosphere, the velocity of the ocean, and the pressure term, as well as what is called the geopotential. And this type of system was studied in a series of papers in the 90s by Lyons, Temam, and Wang, and they proved the existence of a weak solution. It's not known until today. It's like Navier-Stokes, whether this weak solution is unique or not. It's also a difficult open question. So what is our approach to this type of equation? So I would like to describe and to discuss very different approach aiming for strong solutions. And this is now related to what we call an optimal data result. So what we are doing, so we collect all the linear terms on the left-hand side, and we write the nonlinear terms on the right-hand side of the equations. And then we are aiming for a result on the linear equation. So we have on the left-hand side here the linear equation including boundary conditions. And we write just functions on the boundary and functions on the bulk on the right-hand side. And we would like to see that what type of conditions on the right-hand side, what type of conditions in F and in the boundary conditions B are needed to guarantee a strong solution. So what do we mean a strong solution? We would like to have a solution where we gain one derivative in time and we gain two derivatives in space. Yeah, so that's is usually called a strong solution. And the result over here tells us in order to have a solution of this coupled atmosphere-ocean problem, we need, if we have a strong solution, then it is necessary and sufficient on the data that they satisfy this, if you see it the first time, probably complicated looking function spaces, but it means, so the right-hand side F, the force needs to be an LP function. The initial data for strong solution belongs to a usual Bezoff space. And the boundary data, if you choose P and Q equal to 2, belong to H1/4, roughly speaking. If you do the PQ setting, you see this more involved function spaces appearing here. So that's the linear part. And once we are having this once we're having this optimal data result, we can prove by a fixed point argument, by a contraction principle argument, that the system has a unique strong solution. So what is the main difficulty? We have to estimate the coupling term, the nonlinear coupling term in the space coming from the boundary terms. And we saw before they are in the simplest case H1/4, or they are these F spaces, these Triebel-Litzolkin spaces. And then one has to do a para product estimate in these spaces. So if one does that, then we get a unique local strong solution. And the space of initial data is then natural for strong solution. And we can develop a blow-up criterion in the sense we can show if T plus is the maximal time of existence. And if we assume that T plus is finite, then the velocity of the atmosphere and the velocity of the ocean does not belong to this LP space. So if we see it the other way around, if we can show that the velocity of atmosphere and the ocean belong to this function space, then we have a global solution. Yeah, and now one can do energy estimates, and they imply that this coupled atmosphere-ocean model has indeed a unique global strong solution. So let me write it down here in some detail. So you can just fix the case P is equal to 2, Q is equal to 2, which it's in here. Then there exists a unique, strong global solution to this coupled system. And it's really a strong solution. It means, so the velocity, the dTV makes sense. And also the Laplacian terms make sense because our solution has in space H2Q regularity. And now one can even do more involved analysis. One can use what is called Antonen's trick and show if the right-hand sides F are CK or even analytic, then the same is true for the solution. And one can do regularity assertions of the interface over here. So what is interesting to remark is if we look at this coupled problem by this type of methods, aiming for strong solutions, so we get in particular an answer to the original problem posed by Lyons, Temam, and Wang, saying there is a unique global strong solution to this problem. Good. Now we make the problem a bit different and we switch a bit the point of view. We would like to incorporate stochastic forces in this model. So, and now we can do two types of stochastic forces. We can look either at stochastic forces on the boundary, or stochastic forces can be in the transport noise. And now this is some modeling coming from the school of Maida particular. And let me discuss how we derive this transport noise, or how we derive this new type of equations. So we start with the compressible Navier-Stokes equations. And again, we assume that they are anisotropic. So if you start with the standard Navier-Stokes equation, again, we assume that the horizontal diffusion coefficient, viscosity coefficient, is different from the vertical one. And then we have a state equation for the density, and we have an anisotropic temperature equation. Again, here, the coefficients for the temperature in horizontal direction and vertical directions are different. And now the first main point over here, which is new. Usually one does Boussinesq approximation. And here we are dealing with what we call then a stochastic Boussinesq approximation. And roughly speaking, what we are doing, we approximate all terms with density, with noise, except the buoyancy force. So if you want to do it in formulas, so we approximate all terms where there is the density, and we assume the density is close to a constant. We approximate by a noise, where the beta n are Brownian motions. And we see that this is somehow consistent with the usual deterministic theory, where we replace it by 0, and here the expected value of these terms are equal to 0. So then we have a new type of equation. And now if we do that, then we have an equation for u, which is written in the first line over here. And then as before, for the hydrostatic approximation, which we discussed before, we do a scaling for horizontal and vertical velocities. And then we get a new equation for the vertical velocity. And again, there's now in the bracket, there's a term epsilon squared times these terms involving vertical derivatives. And now, following what we did in the deterministic case, one can now do a stochastic hydrostatic approximation, meaning that we assume that the limit epsilon going to 0 of the blue terms are equal to 0. And then doing this, we end up with a new equation, which are the non-isothermal primitive equations. And now this is a stochastic PDE. And you see the deterministic parts are as before. And then we have now a probabilistic part described by Brownian motions beta n. And we have the noise acting on the transport term over here. Therefore, the name transport noise. So instead of a deterministic transport equation, we are having now a probabilistic transport equation with the phi n's and the psi n's over here. Yeah, so we have now a new type of primitive equations coupled to temperature and based on this stochastic Boussinesq approximation. And now one would like to see whether one can solve also this new type of equations. And let me comment a little bit on the main difficulties in the situation before. to get this blow-up criterion working, we had L infinity H1 bounds for the temperature and L infinity H2 bounds for the velocity. Now we need more higher order bounds, so we need L infinity H2 bounds also for the temperature. And these are typical energy bounds, but for higher norms, and one has to work now a bit more compared to the deterministic situation to obtain these bounds by energy estimates. I will not give details here how to get these energy estimates, but now let me comment on the result. So we have this stochastic primitive equation with transport noise, and we assume that the noise functions phi j are L infinity taking values in H1 3 plus delta. And then we get a, not so surprising, we get a unique local pathwise solution to this new equation subject to transport noise. And one can prove that this local solution can be extended to a global pathwise one, provided the noise functions phi n1 and phi n2 are independent of the vertical direction. Okay, so maybe some comments, some remarks. So if we now say there is no stochastics if the phi n are equal to 0, so no stochastics, we get the classical result due to Kao and Titi on these primitive equations. So now following the idea we had before, we look at the linearization of this problem. And if we now look at the linearization, we see that we have a deterministic part, which we understand quite well. And we have now a stochastic part. It's the Helmholtz projection applied to a noise function times gradient V. And then we see this stochastic part is equally strong than the Laplacian term. And hence we are looking for what is called stochastic maximal regularity approach to that. And if one does the details for that and does the energy estimates, we see that we get even a global pathwise solution provided these noise functions phi n are independent of the vertical directions. Yeah, so this is our result on the primitive equation with transport noise. And let me switch to the second version of the stochastic component. Now we would like to have this, the wind-driven boundary condition described not in the deterministic setting, but described in the stochastic world. So for this, we choose a Wiener process W, and which is adapted. And then we look at the equations, which are the usual primitive equations, which we recall. So it's V plus the nonlinear term for the primitive equation in horizontal variables and the nonlinear term in vertical variables. We have Laplacian V and the horizontal gradient of the pressure. And then we have a Brownian motion and a cylindrical Wiener process on the right-hand side, which is not the main issue here, but we would like to have stochastic boundary condition modeling the wind. And how do we do that? Before we had that V is equal to 0 or is equal to this deterministic wind-driven boundary conditions. And now we say they are equal to dTW, and W is again a function of coefficients G, En times another cylindrical Wiener process WB over here. So now this we mean by we have a stochastic wind-driven boundary condition. We have a stochastic process on the boundary coupled to this primitive equations. And what is our strategy? What is our strategy? We eliminate the pressure term, usually by the Helmholtz projection, and then we look at this as a semi-linear stochastic evolution equations. And as before, we have then the hydrostatic Stokes operator over here. and we have the bilinear term here. So what we are aiming, we are following what is called often the Pareto-Sapchik or the Pareto-Debouche trick. So we look at a solution of this differential equation subject to stochastic boundary condition by a term which is by a solution by a term which is described over here. Here we see, so A is the usual hydrostatic Stokes operator. N is called the Neumann operator. And the Neumann operator is, again, a classical topic in analysis. So it maps deterministic Neumann data to the solution to the hydrostatic Stokes problem. So if we follow this approach, we can see that the stochastic boundary condition can be understood as a forcing term on the right-hand side. So that's a good strategy then. If one goes more into detail, then one sees the term in the brackets over here. They need to belong to the domain of the operator A, to the Stokes operator. Yeah. However, the Neumann mapping does not respect the boundary condition of the Stokes operator. So one way out is to go to a weaker setting. And yeah, we would like to have that the term in the bracket belong to the domain of the Stokes operator A. And one way to do that, we go to a weaker setting, saying we go to a Sobolev space of negative order a little bit. And a little bit means we go up that much that the boundary condition is not seen anymore. Yeah, meaning we choose now an anisotropic ground space, which has different regularity in horizontal. That's the usual Sobolev space. But in vertical direction, we go to a negative scale S-2 for appropriate S. And this can be done. There's a theory that this type of equation can be shifted to extrapolation scales, and this we are using. And then the linear part behaves nicely in this extrapolation scales, also in this Sobolev space of negative order. However, we also have to deal with the nonlinear estimates now. And this is more tricky, and we do not even know in detail how to do. So if you look at the Navier-Stokes nonlinearity, then estimates in H-1 are okay. Now we have the primitive nonlinearity, which has one more derivative. So it's a stronger nonlinearity. And we do not know how to do energy estimates for global solutions in the setting of negative spaces. However, we get at least a local solution for the primitive equation subject to stochastic wind-driven boundary conditions. So if we allow us to go to a negative space, let's say to H-1p, then we get a local well-postness result over here. I wrote down an open question is we do not know whether we can extend this local solution to a global one, because a priori estimates or energy estimates in negative spaces for this primitive nonlinearity are tricky, and we do not know how to do. Okay, now we switch topics a little bit again, coming back to this original problem by Lyons, Temam, and Wang. They started with the primitive equations in the compressible setting. And in their paper, they use the pressure coordinate approach. What we are doing here, we are trying to look at the compressible situation in more detail in Lagrangian coordinates. So now we have, again, a system. We have dt plus divergence rho u is equal to 0. Again, rho is density, u is velocity. And then we have the momentum equation where the material derivative is described here. And then we have a Lamé, usual Lamé operator in here. And then we have the horizontal gradient of the pressure is equal to 0. And the pressure and the vertical derivative of the pressure is given by gravity times density, and the pressure is related to the density by a power law, rho to the gamma. And what I will be doing here, I will look at the particular case to make things less technical. We look at the case gamma equals to 1, which corresponds to the ideal gas law that P is proportional to rho. So how can we now solve this type of equation? We do a variant of the Lagrangian transformation, which is well known in compressible fluids. Here now we introduce a new version of the Lagrangian transformation, which we call hydrostatic. So instead of the velocity, we take here v bar, which is the average velocity over here. And then one can solve this equation here, and one makes the usual change of variables. And then one gets the equation now written in hydrostatic Lagrangian coordinates. This has the advantage that we simplify the continuity equation to a large extent. That was our aim. The price we have to pay, that the momentum equation is getting more difficult. As you can see here, the Lamé term now does not have only constant mu and mu prime, but it has functions coming from the transformation. So here we gain that the continuity equation is simpler. However, the equation for the velocity has now a complicated Lamé operator in between. And now how do we define the hydrostatic Lamé operator? Yeah, we have the usual Lamé operator, but now with coefficients coming from this transformation. And we are interested in this new Lamé operator, which we call the hydrostatic Lamé operator. So hydrostatic coming from Lagrangian transformation. And then we have these coefficient functions A and B inside the Lamé operator. And now one can do some kind of Fourier analysis, harmonic analysis, to show that this hydrostatic Lamé operator has a bounded H infinity calculus, has maximal regularity property, and all the properties we would like to have. So one can do that because this operator is parameter elliptic, and one can do perturbation theory. So if we believe that for a second, we get a local well-postness result for these primitive equations in the compressible situation. So we have then natural conditions on the two initial data, psi naught and v naught, and we get a local strong solution. And again, we would like to see whether it would be possible to extend this local strong solution to a global one. And then we modify slightly our hydrostatic Lagrangian transform. So we subtract a value, the mean value of psi, and then we can linearize around this new term. And then, as in the situation of compressible Navier-Stokes, the linear part is then governed by the compressible Stokes operator. And here we have the hydrostatic situation. Then it's now an object defined on the product space H1Q times LQ. And on the diagonal, we have 0 here, and then we have the Lamé, and here we have the hydrostatic Lamé operator. And on the off diagonal, we have the horizontal gradient and the divergence over here. Okay, now one can also show that this hydrostatic Stokes operator has again nice properties coming from harmonic analysis. It allows a bounded H infinity calculus. And if we restrict to the mean value free spaces, we see that the corresponding semigroup is even exponentially decaying, and hence we get a global solution. And that's the result for a global solution. So if we assume that the initial data are small, then we get that these compressible primitive equations admit also a unique global strong solution living on the whole R plus line. And the solutions are then exponentially decaying. Maybe one last comment to the beginning, where we studied this model coming from Lyons, Temam, and Wang. And now we are ready to look at the compressible, incompressible model. Now we take the compressible primitive equation for the atmosphere, we take the incompressible primitive equation for the ocean, and we have our wind-driven boundary condition in the deterministic setting. We already understood that. And now one can do what we just did. We can introduce Lagrangian coordinates. And then doing that, one can combine the hydrostatic situation in the compressible and incompressible situation. And like this, one gets a local strong well-posedness result for large data. And if the data are small, one gets, in addition, that we get a global strong well-posedness result for small data. This is somehow natural because all this is also not more is known in the situation of the usual compressible Navier-Stokes equation. I guess this is a good point to finish my talk over here. Here you can see some references about the results I was talking, and thank you very much then for your attention.
Thank you, Professor Hieber. Thank you very much. Guys, do you have any question to Professor Hieber? I would like to know about, well, you're dealing now with this part that has the winner process. If you have some data or a numerical analysis available that you can say that this improved the results in qualitative way in comparison to deterministic.
Yeah, very good question. Very good question. But I'm afraid I do not have a good answer. It's more, let's say, a mathematical study. We don't have numerical evidence or experimental evidence saying that the data are of this form and therefore we get better results over here. There are people like the Peter Kohn in Hamburg in Germany. They are really doing this type of models from the very applied side, and they might have data and they collect data and they do models depending on their data. But here, I'm afraid I cannot say a lot about this.
Mm-hmm. And when you deal with the equation, when you go to the integral form, do you use Ito integral?
It's both. It's Ito integral or Stratonovich noise. Both works.
Okay.
Yeah, both.
Okay, both of them. Okay, great. Guys, do you have other questions or comments or anything? I loved your talk. Thank you very much. Thank you for the clear exposition for us. I think that we can go to our second talk now. Thank you, Professor Hieber, for being with us.
Thank you.
Very honored to have you here.
Thank you very much for listening, and it was a great pleasure and honor for me to give this talk in your seminar. Thank you. Okay, so